Researchers right here in California are tapping into the state's largest fault line to help predict future earthquakes.
A massive quake on the other side of the world is really shifting our understanding of the San Andreas Fault.
The San Andreas Fault has once again captured attention, not because of the typical tremors and gradual shifts it is known for, but because of something far stranger. Without any immediate warning, subtle activity was detected that did not align with the normal patterns scientists have come to expect. The San Andreas Fault is one of the most closely watched geological structures in the world, with instruments scattered across its length, each designed to detect the smallest of movements. Yet this time, what surfaced was not a typical earthquake, nor the regular slow slips that geologists have cataloged for decades. Instead, it was a burst of unusual signals, activity that stood apart from what models had predicted, sparking questions about whether one of the most feared possibilities could be closer than anyone had anticipated. Before we start, hit the like and subscribe buttons for more updates. What makes this development stand out is the sheer unpredictability of it. Earthquakes along the San Andreas Fault usually announce themselves in specific ways, with precursory tremors, subtle changes in pressure, or recognizable seismic swarms. This latest occurrence seemed to bypass those telltale signs. The ground shifted in ways that could not easily be categorized, and seismographs recorded irregular waveforms that didn't match familiar earthquake templates. For experts who spend their careers studying the fault, such an anomaly sets off alarm bells because unpredictability is precisely what makes the San Andreas so dangerous. A sudden, unexplained signal can suggest processes unfolding deep beneath the crust, ones that humans are not yet equipped to fully understand or forecast. The fear tied to this anomaly stems from what is already known about the San Andreas Fault. Stretching roughly 750 miles through California, it forms the boundary between the Pacific Plate and the North American Plate. It is, quite literally, a scar that defines the state's geography. Historical records reveal its catastrophic potential, most famously with the 1906 San Francisco earthquake, which devastated the city and left lasting scars both physical and cultural. Since then, countless studies have focused on the likelihood of another rupture along different sections of the fault. The southern portion, running through Los Angeles and into the desert, has been locked for centuries, accumulating immense stress. Scientists refer to this locked segment as the place where the big one is expected, a massive quake that could reshape the region. The recent unusual activity raises questions about whether such a feared event is approaching faster than anticipated. The way this activity emerged adds to the tension. Normally, slow slip events occur quietly, releasing built-up energy gradually over days or weeks. These slow movements are detectable but rarely damaging, and they can sometimes even help to delay a larger quake by relieving stress. But what has just been observed did not behave like a slow slip. Instead, it appeared as a sudden cluster of signals, localized but intense, as though something beneath the fault had shifted unexpectedly. If these were merely small tremors, they would be cataloged and studied like thousands of others. But their irregular patterns suggest they may be part of a deeper process, one not yet clearly understood. This lack of clarity is what unsettles both scientists and the public because it points toward blind spots in seismic knowledge. At the heart of the concern lies the possibility that these signals are a sign of stress redistribution along the fault. In geological terms, when pressure builds up in one section, it can be transferred elsewhere, setting off a chain reaction. A sudden and unexplained signal might indicate that stress has been moved in ways that could prime another section of the fault for rupture. The idea that this could be happening without any warning undermines much of the confidence built around earthquake preparedness. Modern seismology relies on identifying patterns, on connecting present tremors with historical behavior. When something arises that does not fit the pattern, it reminds everyone of how incomplete human understanding of Earth's mechanics truly is. Adding to the unease is the broader geological context of California. The state is riddled with faults, many of which connect to or interact with the San Andreas. Movement in one can influence another, sometimes in subtle ways, sometimes catastrophically. The Ridgecrest earthquakes of 2019, for instance, reminded people that even smaller fault systems can trigger significant seismic chains. If the San Andreas is showing signs of unfamiliar activity, it raises the possibility that its neighboring faults could also be under unusual stress. This interconnectedness transforms any anomaly into a potential precursor for a wider seismic response, amplifying the fear of cascading effects. The unpredictability also disrupts the fragile balance between scientific reassurance and public anxiety. For decades, experts have emphasized that while the big one is inevitable, it is also uncertain in its timing, and California has prepared accordingly with building codes, drills, and communication systems. But when activity emerges that falls outside the expected, that reassurance begins to fracture. It prompts the haunting question: could the feared event happen not just eventually, but imminently? Even if the anomaly turns out to be benign, the mere possibility reshapes the psychological landscape, reminding people of how thin the line is between safety and disaster in earthquake country. What deepens the intrigue is how these signals were first detected. Advances in seismic monitoring have given scientists unprecedented insight into Earth's crust, with dense arrays of sensors that can pick up even the faintest shifts. These instruments recorded vibrations that didn't travel in the same way as conventional earthquakes. Instead of clean seismic waves, they saw scattered, uneven oscillations that pointed to complex movement underground. Some theories suggest this could be related to fluids moving through deep rock, lubricating certain segments of the fault. Others consider whether it represents microfractures forming in the locked section, each one a tiny precursor to something larger. Both possibilities are unsettling because they suggest processes at work that humans cannot easily intervene in or control. The role of unpredictability cannot be overstated. Humanity has grown accustomed to forecasting storms, tracking hurricanes, and issuing warnings for floods, but earthquakes remain stubbornly resistant to prediction. Scientists can calculate probabilities over decades, but they cannot pinpoint exact moments. This anomaly on the San Andreas underscores that limitation, showing how something so significant can occur without fanfare or warning. It forces a confrontation with the uncomfortable truth that one of the most dangerous natural threats may give no clear sign before unleashing its full power. The implications extend far beyond science and into society itself. California's economy, population centers, and infrastructure are tightly bound to the landscape carved by the San Andreas Fault. A sudden rupture along the southern portion could devastate Los Angeles and surrounding regions, disrupting millions of lives. Even the northern stretches, though less overdue, pass close to heavily populated areas like the Bay Area. When unusual activity is detected, the conversation inevitably shifts toward what might happen if the fault were to rupture soon. The fear is not just about the shaking of the Earth, but about the cascading failures it could trigger in transportation, energy, and communications. An unexpected anomaly reminds everyone that these vulnerabilities remain raw and unresolved. Part of what makes this particular moment gripping is the sense that nature does not adhere to human expectations. Models and maps divide the fault into neat segments, assigning probabilities and timelines, yet the Earth itself does not operate on these schedules. An unusual cluster of signals might simply fade without consequence, or it might mark the beginning of a reorganization of stresses that culminates in catastrophe. The inability to know for certain gives rise to speculation and fear, which spread quickly in a world hyperconnected through media and social platforms. A whisper of strange activity on the San Andreas can ripple globally within hours, igniting imaginations and amplifying concern. The scientific community faces the challenge of interpreting this anomaly while maintaining credibility. They must balance caution with clarity, avoiding alarmism, but also not dismissing signals that could be significant. Each irregular pattern becomes a puzzle piece in a vast and incomplete mosaic, one that may only be fully understood after the fact. This reality creates tension between the desire for certainty and the inherent unpredictability of Earth's processes. The San Andreas has always been a symbol of that tension, embodying both the power of scientific inquiry and its limits. The San Andreas Fault has always carried with it a strange paradox. It is at once one of the most heavily monitored and studied fault systems in the world, yet it retains the ability to surprise. The recent unexplained activity highlights how little certainty exists in the field of seismology, despite decades of research, sophisticated instruments, and the accumulation of vast amounts of data. This moment serves as a vivid reminder that beneath California's fertile valleys, bustling cities, and sprawling deserts, lies a restless boundary line between two enormous tectonic plates constantly grinding, sticking, and lurching toward their inevitable release. What makes the latest anomaly unnerving is that it was not heralded by the usual suspects. No foreshocks, no small tremors in tidy progression, just a sudden burst of irregular signals that defied immediate classification. Much of the fascination with this event comes from its location within a fault system already loaded with tension. The San Andreas is not a uniform fracture but a chain of segments, each with its own history of rupture. Some of these segments release strain more regularly, while others, such as the southernmost stretch running toward the Salton Sea, have been ominously quiet for far too long. That southern portion last unleashed a major rupture centuries ago, which, in geological terms, is well beyond the average recurrence interval. The signals now detected may not be located precisely in that locked section, yet any movement anywhere along the fault raises concern about whether stresses are migrating toward areas primed for a catastrophic break. The possibility that pressure is subtly reorganizing itself underground is the kind of scenario that keeps geologists awake at night. What deepens the intrigue is how these signals differ from the ordinary chatter of the Earth. In California, small earthquakes happen daily, most of them so minor that people never notice. They are the seismic background noise of a living landscape. But what was recently captured bore a strange character, resembling neither the sharp jolts of a standard quake nor the rolling oscillations of a slow-slip event. Instead, it appeared to be a hybrid, a kind of in-between that suggested an unfamiliar process unfolding at depth. Some researchers speculate that this could be a sign of creeping movement along hidden subsidiary faults connected to the main San Andreas system. Others wonder whether fluids trapped deep in the crust are beginning to migrate, weakening rocks and creating unpredictable shifts. Both interpretations point toward processes that could alter how stress is distributed, potentially setting the stage for larger ruptures in ways that science has yet to map with precision. The public tends to think of earthquakes as discrete, dramatic moments, seconds or minutes of violent shaking followed by aftermath and recovery. But beneath that drama is a continuum of motion, much of it invisible, silent and gradual. These latest signals force people to confront that hidden world, one where vast amounts of energy are constantly stored, transferred, and occasionally released. The fear is that if energy is being moved in an unexpected way, it may be accumulating in the wrong place, silently winding the spring tighter. When the spring finally snaps, the consequences could be staggering. This is why any anomaly along the San Andreas resonates so profoundly. It is not merely about what has just happened, but about what could follow. The psychological dimension of this cannot be underestimated. Californians live with a collective awareness of the San Andreas, woven into the culture through films, school drills, news reports, and even casual jokes about the big one. Yet beneath the humor lies a real undercurrent of anxiety, a recognition that the fault is a permanent shadow over daily life. Anomalies like the recent one stoke that anxiety by breaking the rhythm of normalcy. People can adapt to a steady drumbeat of small tremors. They know the ground shakes occasionally and life goes on. But when something unpredictable surfaces, it cracks the veneer of control and raises the unsettling prospect that disaster may come without the familiar precursors. This shift in perception alone is powerful, as it changes how communities interpret every small shake that follows. Beyond the cultural and emotional response, there is the challenge for scientific interpretation. Each time an anomaly arises, researchers must piece together data from a sprawling network of instruments, seismometers, GPS trackers, satellite imaging, and more. They must decide whether the signals are noise, harmless slips, or genuine precursors of something larger. The complexity of these interpretations reflects the broader mystery of earthquake science. For all the progress made, prediction remains elusive. Probability maps can outline risks over decades, but they cannot tell whether a sudden irregular signal is a warning or just a geological curiosity. This limitation means every anomaly becomes a test case, an opportunity to learn, but also a reminder of how blind humanity remains to the deeper workings of the Earth. Another dimension worth considering is how this unusual activity interacts with broader tectonic dynamics beyond California. The Pacific Plate and North American Plate are locked in a slow but relentless dance, their grinding motion shaping not only the San Andreas Fault, but also the network of related faults stretching across the western United States. Some of these faults extend offshore, while others crisscross deserts and mountains inland. The recent anomaly, therefore, cannot be viewed in isolation. It may be part of a larger story unfolding along the entire plate boundary, a story that links California to global seismic processes. If stress is shifting in unanticipated ways here, it may mirror or influence changes along connected systems elsewhere. This interconnectedness adds another layer of uncertainty, as the Earth rarely behaves in isolation. One region's anomaly can ripple outward, subtly influencing distant faults in ways still poorly understood. The practical implications of this are immense. California's infrastructure, from bridges and highways to water systems and energy grids, has been designed with earthquakes in mind. Yet most of that planning rests on models built from known patterns, recurrence intervals, mapped fault segments, and familiar types of tremors. When something happens that falls outside of those patterns, it raises the unsettling question of whether infrastructure is prepared for scenarios not yet imagined. Could a rupture unfold in a way that engineers have not modeled? Could cascading shifts trigger failures across multiple systems simultaneously? These are not idle questions, for the resilience of entire cities depends on anticipating the unexpected as much as the expected. The unusual activity also sparks debate about the role of human activity in influencing seismic systems. While the San Andreas Fault itself is a natural phenomenon driven by tectonic forces, scientists have long observed that human actions such as deep wastewater injection or geothermal energy extraction can sometimes trigger minor quakes in other regions. Could it be that industrial processes near the fault are interacting with natural stresses in subtle ways? While no evidence yet ties the latest anomaly to human influence, the question underscores how delicate the balance of forces can be, and how easily that balance might be perturbed. It is a reminder that humanity does not merely live near these geological systems, but also interacts with them, sometimes knowingly and sometimes inadvertently. Equally important is how this event reframes the conversation about monitoring and early warning systems. California has invested heavily in Shake Alert, a program designed to give residents precious seconds of warning before strong shaking arrives. Yet Shake Alert, like all early warning systems, relies on recognizing familiar seismic signatures quickly enough to trigger alerts. When signals do not match known templates, as in the case of the recent anomaly, the system's effectiveness may be compromised. This raises the urgent question of how adaptable such systems are to the unexpected. Can machine learning and artificial intelligence be harnessed to detect patterns that humans cannot yet define? Could future monitoring systems learn from anomalies to better prepare for the truly unpredictable? These questions reflect a frontier in seismology that the San Andreas may be forcing into sharper focus. The global dimension of this cannot be ignored either. Around the world, other fault systems carry risks similar to or greater than those of the San Andreas. The North Anatolian Fault in Turkey, the Alpine Fault in New Zealand, the Himalayan thrust zones, and countless others. Anomalies detected in California resonate internationally because they highlight the universal problem of seismic unpredictability. Scientists in other countries watch closely, seeking parallels to their own fault systems. The fear of the big one is not limited to California. It is a human fear shared by all who live near active faults. The recent event underscores how unprepared humanity remains, despite technological advances, for the sheer force of the Earth's restless plates. What makes the San Andreas particularly symbolic, however, is the scale of human exposure. Tens of millions of people live within striking distance of its rupture zones. California is not only a cultural hub, but also an economic powerhouse, and any disruption along the fault carries global consequences. The unusual signals recently detected may not have caused any immediate harm, but they rekindle the awareness that the margin between stability and chaos is razor thin. The daily hum of life in Los Angeles, San Francisco, and countless smaller communities continues. Yet beneath it all lies the silent reminder of a fault system capable of rewriting that daily rhythm in seconds. This juxtaposition of ordinary life and extraordinary risk is part of what makes the San Andreas such a potent symbol of human vulnerability. At the same time, this event emphasizes the value of humility in the face of natural forces. For all the progress humanity has made in building skyscrapers, spanning canyons with bridges, and networking the world with fiber optic cables, the San Andreas shows that the ground itself can upend all of it in an instant. It is a reminder that no matter how advanced civilization becomes, it remains subject to the rhythms of the planet. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on the San Andreas Fault showing strange activity recently? We want to hear from you. Thank you for watching, and see you next time.